Welcome back to this class of General Statistics. Today I'm going to start the chapter on probability. I call this one part 1. Okay, the topic I'll be covering in this video is probability rules. The first one. The second one is computing and interpreting probabilities, and independence and multiplication rule. All right, so let's start with the probability rules. Introduction. Probability is a measure of the likelihood of a random phenomenon or chance behavior occurring. Probability describes the long-term proportion with which a certain outcome will occur in situations with short-term uncertainty. Probabilities deals with experiments that yield random short-term results or outcomes, yet reveal long-term predictability. The long-term proportion in which a certain outcome is observed is the probability of that outcome. So this is a sort of introduction to probability. And this is very important. The law of large numbers. As the number of repetitions of a probability experiment increases, the proportion with which a certain outcome is observed gets closer to the probability of the outcome. All right, so let's go into some definitions. In probability, an experiment is any process that can be repeated in which the results are uncertain. The sample space, usually denoted as capital S, of a probability experiment is the collection of all possible outcomes. Then we have what we call an event. This is any collection of outcomes from a probability experiment. An event may consist of one outcome or more than one outcome. We will denote event with one outcome, sometimes called simple event, okay, with small e. But in general, we use capital E to denote event. All right, so how do we identify events and the sample space of a probability experiment? So let's consider this example. Consider the probability experiment of having 2 children. Just 2 children. Question 1, identify the outcomes of the probability experiments. Determine the sample space. And last question, define the events E, which is have 1 boy. All right, so let's identify the outcomes first. E, little E1 is boy. There's a possibility of having boy and boy. There's a possibility of having boy and girl. There's a possibility of having girl and boy. And then lastly, girl and girl. So what is the sample space in this case? The sample space S is the set of all these possible outcomes. So boy, girl, boy, and girl. Now, if you are interested in choosing, in defining an event E of 1 boy, this will be each category with a boy. So we have this one as a boy and this one as a boy. So the probability, the event E is just a set containing 2 elements, boy, girl, and girl, boy. All right, so let's go into the rules of probabilities. The probability of any event E, which we denote as P of E, must be greater than or equal to 0 and less than or equal to 1. So, in other words, 0 is less or equal to P of E and less or equal to 1. It could be 0, it could be 1, or any number in between. Anything outside this range is no longer a probability. Rule 2, the sum of the probabilities of all outcomes must equal 1. When I take all the possible outcomes and I find the probability and I add all the probabilities together, they must be 1. So suppose we have sample space with event E1 to En, then probability of each of these guys, when I add them together, I should get 1. All right, so what is a probability model? A probability model lists the possible outcome of a probability experiment and each outcome's probability. So a probability model must satisfy rule 1 and 2 of the rules of probabilities, as we've stated in the previous slide. For example, in a bag of peanut M&M milk chocolate candies, the colors of the candies can be brown, yellow, red, blue, orange, or green. Suppose that a candy is randomly selected from a bag. The table shows each color and the probability of drawing that color. Verify this is a probability model. So we have this table, color and probability of each, and we need to verify if this table represents a probability model. First, check each of the probabilities. This is 0.12, 0.15, 0.12, 0.23, 0.23, 0.23. Clearly, none of this is outside 0 and 1. All the numbers are within 0 and 1. The sum of all probabilities is equal to 1. So if you add all these numbers together, what we get is 1. So both rules are satisfied. Therefore, this is a probability model. All right. If an event is impossible, the probability of that event is 0. Okay? If an event is a certainty, the probability of that event is 1. Now, you need to be careful with this. An event is unusual if it has a low probability of occurring. Usually, 0.05 is regarded as the threshold, but this can be different depending on the textbook. For us, we are going to be using 0.05 as the cutoff point. All right, so what is empirical approach? The probability of an event E is approximately the number of times event E is observed divided by the number of repetitions of the experiment. So this is empirical because it has to do with observation. And this is very close to what we learned before. It's just the relative frequency of E. All right, for example, so Pass the Pigs is a Milton-Bradley game in which pigs are used as dice, okay? Points are hand based on the ways the pig lands. There are 6 possible outcomes when one pig is tossed. A class of 52 students roll pig 3,939 times. The number of times each outcome occurred is recorded in the table at the right. So we have this table, side with no dot, 1,344, side with dot, 1,294, Razorback, 767, Trotter, 365, Snorter, 137, Leaning Jawler, 32. Let's see the question. Use the result on the experiment to build a probability model for the way the pig lands. Estimate the probability that a thrown pig land on the side with dots. Will it be unusual to throw a leaning jawler? So let's take it one by one. To build a probability model from that table, we have to compute the probability. So remember, the first number is 1344 divided by the total is 3939. That's where we get 0.39. 41. This one corresponds to 1294 divided by 3939. And this one corresponds to 767 divided by 3939. This one corresponds to 365 divided by 3939. This one corresponds to 137 divided by 3939. And lastly, this one corresponds to 32 divided by 3939. Then you just use a calculator to get all these probabilities. Okay, so clearly the sum is 1 and each probability is within 0 and 1. So this is a probability model. B, what's the probability of a true result in a side with dot, which is this one, is 0.329. How do we interpret this? It means that in 1,000 throws of the pig, we expect about 329 to land on the side with dot. That's the interpretation. Okay, so a leading jaw will be unusual. Why is that? Of course, in the previous slide, I said the threshold for unusual event is 0.05, but this is even far less, 0.008. And that is why leading jaw is unusual. What does it mean? We will expect in 1,000 throw of a pig to obtain leading jaw about 8 times. That's very small. All right, so we talked about empirical approach. Now we are talking about classical method of computing probabilities. This requires equally likely outcomes. All right, so an experiment is said to have equally likely outcomes when each simple event has the same probability of occurring. So how do we use classical approach? If an experiment has n equally likely outcomes, and if the number of ways that an event E occurs, if the number of ways that an event E can occur is m, then the probability of E, which is denoted as PE over here, is given as m over n. So the number of ways E can occur over the number of possible outcomes. This is called classical approach. So if S is the sample space of the experiment, then PE is the number of E over number of S in a short form. Now let's look into an example. Suppose a font-sized bag of M&M contains 9 brown candies, 6 yellow candies, 7 red candies, 4 orange candies, 2 blue candies, and 2 green candies. Suppose that a candy is randomly selected, okay? What is the probability that it is yellow? What is the probability that it is blue? Comment on the likelihood of the candy being yellow versus blue. All right, so let's start with answering the questions. So there are a total of how many candies in the bag in the bag? This is total of up to 30. If you add all the candies together, so the number of the sample space is n, is 30. Now, probability of yellow is number of yellow over number of sample S. So here we get, remember yellow, we have 6 bags of it, 6 yellow. So over 30, giving us 0.2. For blue, the same thing. There are 2 blue candies, so we have 2 over 30 in this case, so it's 0.067. All right, so if you want to compare the two, selecting a yellow is 3 times as likely as selecting a blue. Of course, yellow has greater probability. Okay, again, what is subjective probability of an outcome? Okay, this is a probability obtained on the basis of personal judgment. Remember, we started with empirical, we did classical, now this is subjective. This is just based on personal judgment. Example, an economist predicting there is a 20% chance of recession next year will be a subjective probability. And that is going on right now. So in the US, there's everyone is predicting there is a probability of this recession coming up next year, next 2 years. These are subjective probability. All right, so in his fall 1998 article in Chance magazine, a statistician reads the spot page 17 to 21. As Chan investigated the probabilities that a particular horse will win a race, it reports that these probabilities are based on the amount of money bet on each horse. Okay, the question is when a probability, so the question is, what is this probability? Is it empirical, classical, or subjective? Of course, this is based on the money, okay? So it's giving that a particular horse will win a race. In this, this is subjective because it's based upon people's feeling about which horse will win. You are betting the money right now. All right, so the probability is not based on a probability experiment or counting equally likely outcomes. So we cannot say it's empirical or classical. Good, let's go to a very important concept in probability. This is called disjoint event. Two events are disjoint if they have no outcomes in common. And sometimes this is called mutually exclusive. Okay, so Venn diagram is usually used to represent such this type of thing. All right, and this is enclosed with a rectangle. The rectangle represents the sample space, and each circle represents an event. Okay, so when I have two events that are disjoints or mutually exclusive, then what will be the probability of E or F? Good news here, this is called addition rule for disjoint events. The probability of E or F is given as probability of E plus probability of F for E and F disjoint. Okay? Of course, this can be extended to more than two events, two disjoint events, and the same formula extends to that. So probability of E or F or G or and so on is equals to probability of E plus probability of F plus probability of G plus probability of, and so on. All right, so let's quickly go through an example. Suppose we randomly select a chip from a bag where each chip is in the bag is labeled 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And then we want E to represent events. Choose a number less than or equal to 2. So it means that E will be a set consisting 0, 1, 2. All right. So immediately we can see that the number of E is 3. How many elements in E? All right, so F represents the event. Choose a number greater than or equal to 8. So event F will be 8 and 9. In this case, the number of F will be 2 because there are 2 elements there. This event are disjoints, okay? So 0, 1, 2 for event E, 8 and 9 for event F. So nothing is in common. So we say they are disjoint, and you can see from the picture how to represent this. All right, so the probability of numbers between 0 and less or equal to 2 is going to be number of E over number of X. So there are total number of 10 numbers. There are 10 numbers involved. So number of S is 10 and the number of E is 3. So we have 0.3. Probability of F, the same way, we have 0.2. Now, probability of E or F, based on the formula we had before, is the probability of E or F over probability of S. And you know that probability of E or F is this plus this. Sorry, number of E or F is 0, 1, 2, 8, 9. So again, I want to iterate that when you see or, this means union. And when you see and, this means intersection. So E or F will be union E, union F, which is 0, 1, 2, 8, 9. That is the number of E or F, then give us 5. And if we divide it by the number of S, we get 10. 5 over 10, which is 0.5. Now let's check with the formula for these joints. If we want to go directly with the formula, we will have set probability of E plus probability of F. Of course, probability of E is 0.3, as we found here, and probability of F is 0.2, as we found here. And if you add it together, you have 0.5. So the answer are the same, which confirm the formula. All right, another example, the probability model to the right shows the distribution of the number of rooms in housing units in the United States. Okay, verify that this is a probability model. What is the probability a randomly selected housing unit has 2 or 3 rooms? What is the probability a randomly selected housing unit has 1 or 2 or 3 rooms? Okay, so let's start from the first one. Clearly, all the probability given in this table, none of them is below 0 or above 1. So this satisfies the first rule. And of course, if you add all the numbers together, you will get 1. So this is a probability model. Now, let's look at probability of 2 or 3 based on our the probability of disjoint events. We have probability of 2 plus probability of 3, and probability of 2 from here is 0.032, probability of 3 is 0.093. So when we do the addition, we get 0.125. The last question here says what the probability of 1 or 2 or 3, which is the addition of the probability. So again, add 0.010, 0.032, and 0.093. If I add all those together, I am going to get 0.135. Okay, now if the events are not disjoint, should that mean that we should just walk away? No. When the events are not disjoint, it means they have something in common. And so the probability of E or F is given by probability of E plus probability of F. Then we have to subtract the probability of what is common. That is the difference. In the disjoint event, this probability is also always 0 because nothing is in common. All right, so let's quickly go into an example. Suppose a pair of die are thrown. Okay, so let E, the first die is 2. Let F, the sum of the die is less than or equal to 5. We are interested in finding the probability of E or F. All right, so first, let's look at event E. So the probability, okay, first, what is the event E? Event E at the first die is 2, is a 2. So the first die here is a 2, 1. The first die here is a 2. This. So we have 6 possibilities. So the probability of event E will be 6 over the total number of dice here is 36. Now let's look at F. The sum of the die is less than or equal to 5. So let me go through each one and see which one the sum will be less or equal to 5. 1 plus 1 in the first place, 1 plus 1 here gives 1 plus 1 here gives 2, which is less than 5. 2 plus 1 here is 3, which is less than 5. 3 plus 1 here is 4, which is less or equal to 5. 4 plus 1 here is 5, is also in the range. 1 plus 2 here is 3, is also in the range. 2 plus 2 here is 4, is also in the range. 3 plus 2 here is 5, is also in the range. 1 plus 3 here is 4, is also in the range. 2 plus 3 here is 5, is also in the range. So, and 1 plus 4 is also in the range. We've exhausted the whole thing. So, how many are these? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So the probability of F will be 10 over 36. Now let's see if there are anything in common. Wherever you see the the circle with the 2 lines, that will be the intersection. We can see the intersection occurring here. 1. Intersection occurring here, 2, intersection occurring here, 3. So the probability of E and F, I said, and implies intersection. So that will be how many of them? 1, 2, 3, 3 over the total number of the sample, which is 36. And so the probability of E or F that we are interested in becomes the probability of E plus probability of F minus probability of E and F. And in this case, this is 6 over 36 plus 10 over 36 minus 3 over 36, which is 13 over 36. All right, so I just give this explanation. The next slide gives the results fully. So we did this. Okay, so probability of E is 6 over 6, which is 1 over 6. 6 over 36, which is 1 over 6. Probability of F is 10 over 36. Probability of E and F is 3 over 36. And then when you do the sum, you get 13 over 36 for the probability of E or F. All right, so let's talk about complement of an event. Let X denote the sample space of a probability event experiment, and let E denote an event, okay? The complement of E denoted by E to the C is all outcomes in the sample space X that are not outcomes in the event E. So if we let E represent any event, E complement represent the complement of E. This is the key. The probability of the complement is 1 minus probability of E. And diagram-wise, this is the way to really understand what is the complement. So this is E. E is the entire thing in the circle, and anything outside E is E complement. All right, so let's quickly take example here also. According to American Veterinary Medical Association, 31.6% of American households own a dog. What is the probability that a randomly selected household does not own a dog? Okay, so that is a complement to the event of household owning a dog. So probability of people do not own a dog is 1 minus probability of people owning a dog, household owning a dog. And of course, the probability of owning a dog is 31.6%, means 0.316. And then when you do the subtraction, you get this. So 68.4%. All right, so another example here, the data to the right represent the travel time to work for residents of Hartford County. All right, so people who live in Hartford County, they are working. The travel time to work is given in the table. Okay, so less than 5 minutes, people travel to work less than 5 minutes, they are 24,000 plus. Between 5 to 9 minutes, they are 39,000 plus, and so on. What is the probability a randomly selected resident has a travel time of 90 or more minutes? Wow. Okay, first question. Second question, compute the probability that a randomly selected resident, okay, of Hartford County will have a commute time less than 90 minutes. Great, so let's start with the first one first, okay? Remember that first you need to know the total of all the residents. If you add this together, you get 393,186. That will be the total resident population. Okay. Then to find the number of those who travel 90 or more minutes, that is given in the last line on the table. 4895 are the residents the residents that have to travel 90 or more minutes. So the probability for this is given as 4895 over the total, which is 393,186. So the probability is 0.012. Now, clearly, those who travel less is the complement of those who travel 90 or more. So we don't have to go through everything in the table again. Since we know the probability of those who travel 90 or more, we just subtract it from 1 to get the probability of those who travel less than 90 minutes. So 1 minus probability of 90 minutes or more. And we got 0.012 before, so this would be 1 minus 0.12, and that would be, 1 minus 0.012, and that would be 0.988. So independent events. Okay, 2 events, E and F, are independent if the occurrence of event E in the probability experiment does not affect the probability of event F. They don't affect each other. The probability of event E does not affect the occurrence of the probability of event F. 2 events are dependent if the occurrence of event E in a probability experiment affect the probability of event F. All right, so let's take some example. It's good to have some example here. Suppose you draw a card from a standard 52 card deck of cards and then roll a die. Okay, you roll a die, you draw a card. These 2 events. So event E is draw a hat. Event F is roll an even number. Are these events E and F independent? Yes, the answer is yes, because the result of choosing a card do not impact the result of the die toss. Okay. Let's take another example. Suppose 2 40-year-old women who live in the United States, we don't care where they are, they could be anywhere, are randomly selected. The event E is woman 1 survives the year. Event F, woman 2 survives the year. Are these events independent? All right, so these are independent, of course, because the 2 women need not live in the same place. So they are not subjected to the same environmental condition, to the same exposure, to the same things that happen, maybe natural disaster or something. So these are independent events. Now let's look at the same problem, but with different conditions. These 2 women live in the same apartment complex. So women 1 survived the year, women 2 survived the year. Are these independent? I think not, because two women are living together. So they are subjected to the same environmental impact, the same thing. So we will take this as being dependent. All right, so when we have two events that are independent, okay, what is the probability of E and F? The probability of E and F here is the probability of E times the probability of F. So this is a multiplication. All right, so let's look at some example very quickly. The probability that a randomly selected female age 60-year-old will survive the year is 99.186% according to the National Environmental Statistics report. What's the probability that two randomly selected 60-year-old females will survive the year? Okay, so the survival of the first female is independent of the survival of the second female, just like the previous example I gave. So the probability of surviving is given to us, 0.99186. So now let's look at it. Two people are chosen. So probability of first survive and the probability of second survive, with the probability of first survive times probability of second survive, because they are independent. So we multiply the probabilities. And so each of them surviving has probability of 0.99186. So we just multiply the two numbers. So we get 0.9838. All right, so another very interesting example, which is very commonly used in schools. A manufacturer of exercise equipment knows that 10% of their product are defective. They also know that only 30% of their customers will actually use the equipment in the first year after it's purchased. If there is a 1-year warranty on the equipment, what proportion of the customers will actually make a valid warranty claim? Now, the 1 year is given, only 30% of those who buy the product will usually use it in the first year. So the question is, what proportion of customer will actually make a valid warranty claim? Okay. In this case, we assume that the defectiveness of the equipment is independent of the use of the equipment. Since they don't know it's defective in the first place, they will quickly, it doesn't affect whether they use it or not. So the probability of defective and used in the first year, so you have to use the equipment before you know it is defective. So the first year, what's the probability of defective and use? And these are independent events. So we have probability of defective times probability of use. Remember that only 10% of the product are defective. So the probability of defective is 0.10, and 30% of the customer will use the product in the first year. So the probability of use is 0.30. So multiplying those two numbers, we get 0.03. Also, for just as we have it in the case of disjoint, for independent events, probability of E and E1, E2, and E3, and so on up to En is the multiplication of their probabilities. All right, so just to see similar problems in that case, so probability that a randomly selected female age 60-year-old will survive the year is 99.186, according to the same example we had before, but different question now. What is the probability that 4 randomly selected 60-year-old females, now 4, will survive the year? The same rule. Probability of all 4 survive is the probability of 4 survive, and the second survive, and the third survive, and the fourth survive. All right, so, and then all we do is to multiply each probability. So remember that probability of anyone surviving is 0.99186. So we multiply this into 4 places, and that gives us 0.9678. Another very quick example, the same question. Now we are asking, what is the probability that at least 1 of 500 randomly selected 60-year-old females will die during the course of the year? Okay, at least 1 of the 500. So let's start. At least 1 dies means 1 minus at least none die. Okay, 1 minus non-die. At least one dice means 1 minus non-die. And non-die means all survives, which we have the probability, which is 0.99186. So, but probability at all die, all survive, 500. You know, we have selected 500. So we have to multiply their probability to all together, which is the same thing as taking the exponent to 500. And using your calculator, the probability of at least one dice out of 500 randomly selected females will be 0.9832. Now, a quick summary of the probability rules, just to capture the whole thing. The probability of any event must be between 0 and 1, and is given this way. The sum of all the probabilities of all outcomes in the sample space must be equal to 1. If event E and F are disjoint, the probability of E or F is the probability of E plus probability of F. If they are not disjoint, or we don't care about the information, is the probability of E or F equals probability of E plus probability of F minus probability of E and F. If E represents any event and E to the C represent the complement of E, then the probability of the E complement is 1 minus probability of E. And lastly, if E and F are independent events, then the probability of E and F equals probability of E times probability of F. Again, remember that this is not limited to 2 events. It could be as many as possible events. All right, so I'm going to stop here, and I'm going to be recording the next video, which is part 2 of probability, and that will deal extensively with conditional probability. Thank you very much, and hope to see you in my next video. If you have any question, please don't hesitate to drop it. I will get back to you. And thank you for paying attention to this.